about a little bit about amperometry, and again, I'm going to get there eventually, I promise. We're going to do like a little concept, and then we're going to have to do a little waylay into background charge and current. So the amperometry is again a type of voltammetry, because voltammetry just meant we were going to apply a voltage and measure a current, and that's what we're going to do here. So it's a subset of voltammetry. And it is the simplest subset of voltammetry because if we look at, again, E is potential here versus time, we're going to talk first about constant potential amperometry, where we're just going to apply a constant potential. And so, again, sometimes people call this constant potential amperometry, or for the sake of convenience, we're just probably going to call it amperometry. So this is constant potential amperometry. And so one of the advantages of constant potential amperometry is that you don't get a lot of background charging current. But since this is a new concept and we haven't talked about background charging current yet, we have to take a little waylay into learning about background charging current. So every time we apply a potential to an electrode, what happens is, so this is like electrochemist shorthand for an electrode here. So that with the dashes, that's my electrode. This is the surface that fits out into a solution. And in every solution, we have electrolyte, right? And so I'm just going to label these things, as positive and negative kind of charges, et cetera, right? So there's electrolyte in the solution. And what would that electrolyte be? It might be, sodium chloride or calcium chloride, right? So you make buffer, right, with ions in it. In electrochemistry, we call that electrolyte, right? And if you think about the buffer that we normally make in our lab, it's got something like 7 grams, I think, of sodium chloride per liter. That's a lot of salt, right? So your brain is very salty. This is supposed to be ACSF, right? Artificial cerebral spinal fluid. Your brain is salty. That's a good thing for electrochemistry. The buffer is salty. But yeah, so you might just think, oh, we need buffers to like change pH. No, in electrochemistry, it does not work without having ions. We need ions to move, kind of to counter the electrochemistry. So this is just like, there's no analyte here. This is just like, I threw sodium chloride in there, kind of thing. But now if I apply, let's say I apply a positive voltage to my electrode. Well, what's going to happen? Because of electrostatics, right, the negative ions are going to be attracted to the surface, and the positive ions are going to move away from the surface. And so what we're going to end up with, right, is a layer, again, this is if I apply a positive voltage, a layer of ions on the surface, right? And then once we get a layer of ions, they kind of attract, their own sort of layer of ions. There won't be as many of these, though. There'll still be negative ions in here. But this kind of structure here, right, has a name. It's called the double layer. And so this is a very important concept kind of in electrochemistry, that it doesn't matter if I have any analyte. The second I apply a voltage, those ions move around, and the ion movement causes a current. So a lot of times we think of current as being flow of electrons. That's not incorrect, but it's really flow of any charged species. So chloride moving around causes current. Sodium moving around, can cause a current. And so it takes a little while for the ions to rearrange. And as I said, in this kind of, there'll be another layer out here. And out here is what I'll call the bulk solution. So eventually you get far enough away from the electrode, it doesn't see the electric field, and the electric field doesn't bother it. But in this area, right, we'll kind of see we'll end up with more negative ions. So right here where the negative ions absorb, this is called the inner Helmholtz plane. And again, if you go out here, This one is the outer Helmholtz plane. There are other names for this. Sometimes people call this also the diffuse layer. And I think there's somebody else who calls them stern layers. So they have different names. Again, if people are studying for oral exams, learn them all. Because you'll have somebody who uses the other different terminology, and then you don't want that to stump you, kind of thing. But the concept is always this, that in electrochemistry, you're gonna, when you apply a positive voltage, you're gonna get the negative ions moving here and there. But eventually they're gonna reach a steady state, right? So eventually these ions have rearranged themselves, and some may be moving because it's solution, but they kind of cancel each other out. And so if we want to make a graph of what this kind of charging current looks like, the graph of charging current, this is I for current, looks like this. So it's an exponential decay, e to the minus t over RC. And so one must ask the question, what's R? What's C? Right, this is physics, right? You've seen this before probably if you've ever taken a physics class. This is the same capacitor kind of charging equation. Here, R is likely to be, again, related to the solution and how many ions you have. And again, we like to put lots of ions in there so we have very little solution resistance. But C is more interesting. C, right, is capacitance. And capacitance is usually proportional to the area of your electrode. So if you have a big electrode, you'll have a big capacitance. If you have a small electrode, you'll have a small capacitance. And so one of the keys to doing any of the fast electrochemistry techniques I'm going to talk about, not this week, but next week, is that we want this to decay fast. And so if we have a big electrode, the decay might look like that, right? Whereas the one I drew in blue might be more indicative of a small kind of micro electrode. So as we look at background charging current, for amperometry, what I'm going to tell you is this is going to happen probably a couple hundred milliseconds, maybe a second, and then you're going to do amperometry for minutes and you're not going to care, right? Because you're going to be down here. And you're going to be back, where it's basically there's no current, and so it's going to be great, right? You're not going to actually use any data where this is going to come into play. But we're going to return to this concept when we come into FSCB, and then it's a big problem and a big deal, right? Kind of thing, actually, when we get to program later today. It's going to be a big problem and a big deal. And so we want to, the area of the electrode is the biggest issue here. And so, as I said, for amperometry, if we're looking at this charging current over time, as I said, this may be, 1 second or something, and then we're going to do our experiment out here, and essentially, there's going to be 0 background current. So that's a real advantage for this constant potential amperometry experiment. Okay. All right, so I told you we had to waylay into background charging current just a little bit because it's still there in amperometry again. It's always there. It's just that, we're not going to do an experiment on the time scale where it really matters. Okay, so now let's get to actually oxidizing something. So, I'm going to have my electrode. Same old bad drawing of an electrode. Now let's assume we have dopamine molecules sitting out here in solution. Again, there's still electrolyte. I'm not going to draw all of it, but it's gonna be there, right? You know, we always do our things in a highly salty solution, right? So there's dopamine, you know, floating out in the solution at some sort of concentration by our electrode. And so now, in order to get an oxidation, we have to apply, right, some sort of voltage that's greater than the oxidation potential of our analyte. So we've got to, you know, get to the, again, there's this magic thing, when we get to that like level of photomolecular orbital, we can do the reaction. So let's assume we're going to do that, right? We're going to apply a voltage that's greater than the potential that we need to oxidize or reduce the analyte. In this case, we're going to talk oxidation because of dopamine. Well, when we do that, so now I'm going to apply, let's say I'm going to apply plus 0.3 volts, right? That would be plenty to be able to oxidize dopamine. When we do that, any dopamine that happens to be sitting right by the electrode surface, right, will immediately be oxidized to dopamine orthoquinone, right? What about these molecules out there? Well, they will be oxidized if they diffuse to the surface, right? So if they get to the surface, now they'll be oxidized and they'll become dopamine orthoquinone. And so for amperometry, if we were to, again, to look at things versus time, and I'm only going to be plotting here what I'll call the Faradaic current. So that's the current. That's not the background charging current. Again, we're going to assume that that's going to go away in a very short period of time compared to our experiment. But this is our current. And so if we're looking at time, and then somewhere here, we now turn our positive voltage on, our current will jump up, and then it'll come back down, sort of like this. So this is just, again, assuming it's in a solution that just is kind of stagnant. I just plopped it in like a beaker. That's what would happen, right? And so you can kind of see in the picture, all right, this one gets here, and then this one gets here, and that one decides to go that way. And migration's not in your favor here. If you actually know anything about dopamine, they're actually positively charged at physiological pH. But, you know, diffusion will still get them here. And so over time, a larger and larger area around the electrode has fewer dopamine molecules, right? So every time I make a dopamine orthoquinone, remember, this molecule goes away, right? We're not recycling in this experiment. We're going to recycle in cyclical voltammetry. But here we're not recycling, right? So we're using it up. Well, if it gets there, it goes away. If it gets there, it goes away, right? If this one gets there, it goes away. And so now you can see I'm going to have fewer and fewer molecules, or they'd have to travel in, right, from longer and longer distances to get to the electrode. The other thing to remember about electrochemistry is it's what we call an interfacial technique. And that means we only see things happen at the surface. Right here is all we care about. I can't do anything in electrochemistry out there. These molecules have to get here for any magic to happen. And so it's not a bulk technique. It's not like a spectroscopy or something where you're looking at a bunch of things in solution. It's an interface technique, and it must be on the interface for us to see it. So we end up depleting dopamine, and that's why the current comes down. All right, so as I said, not a lot of equations, but I'll throw up one. That's the Cottrell equation here. And again, we'll see a lot of typical things that we'll see in electrochemical equations. Again, if you're taking an oral exam, this is one to know. So this is the Cottrell equation. It describes current that's from molecules diffusing to an electrode. So let's again look at the terms, just so that we're used to terms in an electrochemical experiment. And I've already told you about, right, it's the number of electrons. Oops, let's go with electrons, not electrodes. F is Faraday's constant. We're going to talk about Faraday's constant a little bit. But that's 96,500 approximately. A is our area of our electrode, so that comes into the equations a lot. Again, bigger electrodes give you bigger signals. And so when we design nanoelectrodes in this lab, we are hampering ourselves tremendously. There isn't an equation for current that doesn't have area, basically, on the other side. A's in all of them, right? And so you know when you make a small electrode, you're going to get less current. 'Tis the game. C is concentration. And D here is the diffusion coefficient. Again, so diffusion coefficient comes into, I can't spell. A lot of these, here it's kind of weirdly square rooting, but right, how fast, diffusion coefficients, how fast things can move, right, to the electrode come into play. But what really governs this drop off here is this square root of T in the bottom. And so you could basically make this whole equation into this. I is equal to K, all this other junk, including the square root of pi, which is proportional to T to the minus 1/2. So I showed you the background charging current before, and that was E, an exponential decay. This is T to the minus 1/2, and I'd like to point out that while my drawings are poor, they are not the same thing. And so we will contemplate, and in a few minutes when I get there, we will have to think about which falls off faster, an exponential decay or a T to the minus 1/2. This is a critical concept in electrochemistry, and I'll tell you the answer. But, but it is not an exponential decay. It is a T to the minus 1/2 decay. As it's going along. One thing to know, my favorite diffusion coefficient equation, I just want to make sure I get it in there. The only diffusion equation I actually even ever know is that the distance something can diffuse is equal to the square root of 2 dt. And so, again, we're still diffusion coefficient and time. This is really helpful in estimating, how far something could go. In the brain, I have 10 milliseconds, how far could dopamine go? If you know that the diffusion coefficient is approximately 10 to the minus 6, you could come up with a rough estimate, that kind of thing. And so sometimes if you're thinking about how big a pool am I sampling from? Or how far could this really, this depletion layer kind of really go? It's useful to think about those. Okay, so this is if I put it in a stagnant solution, right? So if I just took a beaker and I put it in a solution and there's nothing going on. But electrochemists aren't that dumb. They don't actually do their experiments typically in a stagnant solution because they know their current's just gonna drop off, right? So let's add in convection. So convection's the right term to use, and that is any type of way, again, to kind of mix the solution. You can get some natural convection sometimes just from little heat gradients, that kind of thing, but that's not what we're going to use here. And typically, if you read the textbook, it would tell you would probably get convection from stirring. But honestly, that's not even what electrochemists are weird. Sometimes electrochemists spin the actual electrode to stir the solution. Rotating disc electrodes, that's a big thing. We don't do them in the brain, but if you start to read widely in electrochemistry, which I hope that you do in this lab, you will see that concept of rotating disc. That is a way to introduce convection. Rather than putting a stir bar in, they actually rotate the electrode. But in this lab, we don't do that either, right? We have a flow cell, right? And so in our lab, we are flowing the solution in one direction past. So I tell you that because sometimes what we do doesn't really line up with what the textbook says. I've never read a fundamental electrochemistry textbook that said, well, if you flow your thing by, and it's always talking about stirring or rotating electrodes and that kind of thing, and you have to know, same thing, right? We're gonna flow. We're going to push electrode things by. So by doing that, we change the picture of what the electrode looks like. So now we're going to be able to push via flow, right, dopamine molecules near the electrode. It turns out you can never quite push them to the surface, and there's a tiny little area, think about your double layer, back to your double layer again, which is somewhere on the order of like 10 nanometers, which is also the size of the double layer. I don't think I actually gave the size of the double layer, but kind of thing. So you can push them right up to here, and then from here, they actually have to diffuse. But it's not going to make a practical difference in these sort of things. But we can push them, and we can be constantly regenerating our concentration out here, right? And so if we do that, and we have flow where we have stirring, right, now we can get a constant current, right? So as long as I constantly replenish the surface with a given concentration, I'm going to get a constant current. The current here, I is equal to NFADC. We already did NFAD. Those all should look all familiar. Again, we see these again and again in just about every electrochemistry equation. We see those. But I want to point out the C here, that I is proportional to C, or I is equal to some, again, constant times concentration. And nothing irks me more than when somebody asks one of my students, is electrochemistry quantitative? And they go, I don't know, and I'm like, no, it is. The current is directly proportional to concentration. If it's not, it's because you have problems in your experiment. It's not because of fundamental electrochemistry. Fundamental electrochemistry says it's quantitative. So again, if anyone's answering a question from another professor, I would like them to start with fundamentals and go, yes, it is quantitative. Oh, but occasionally I get fouling at my electrodes, or I get something else that, I can saturate the surface or whatever, we're talking about. Again, I haven't done anything with absorption yet, and I won't today. This is all diffusion controlled electrochemistry, right? So, yes, there are problems in electrochemistry, and this doesn't always work out, but the fundamental law says the amount of current you get should be proportional to concentration. And I think that's a really good advantage for us, that we should be able to calibrate our electrodes, and figure out current versus concentration, and then be able to use that in a biological system to at least estimate concentration. Remember that. Okay, so let's talk for a moment about what people do with biological electrochemistry and amperometry. That was a lot of fundamentals. The most common experiment people do with amperometry is this one. So imagine this is a cell, and that these are like vesicles that are filled with some sort of neurotransmitter. And so what they do is they come in and they place their electrode. This is going to be my electrode here. I don't have black, so I'll use a different color. And so they place that electrode on the surface, and then they stimulate the cell. Usually they do something like potassium, which opens up a bunch of fusion pores. And what will happen is these vesicles will dock, they'll release their contents, right, and then we'll detect them at the electrode surface. And so when you do that, again, if they're looking at current versus time, they get these little spikes. Again, I should make them all the same size. So they'll get these spikes kind of for amperometry. And what's nice for amperometry, and amperometry only, not for cyclophotometry, you can integrate. So if this is, I'm going to blow up a spike here. You can integrate under the curve. And if you integrate it under the curve, you get amount x in coulombs of charge. So if you integrate current over time, right, this is a current versus time trade, you'd get charge. And from that charge, you can use Faraday's constant, and you can get back, as I said, if you know that's 96,000, approximately 500 moles, coulombs per mole of electrons, you can get back, anyways, to the number of molecules. And so the amperometry technique has been the best technique in biological electrochemistry for trying to figure out vesicular content. or at least how much is released. There's a lot of controversy in the field about whether the whole vesicle is released. But so vesicular content is something they're very good at. They can integrate into the curve. They can tell you exactly how many molecules they oxidized. We can't do that with FSCB. I'm just gonna let the cat out of the bag because we recycle. So we go from dopamine to dopamine orthoquinone, and then we make that back into dopamine. So if I were to integrate under the curve, I could recount the same dopamine molecule again and again and again. But here, we never recycle, right? So we don't double count a molecule. And so that's one of the best things that they're good at doing. The other thing that they do in amperometry is sometimes the things look more like this, rather than just straight old spikes like I showed them there. These they call feet, and they think that's indicative of, okay, I'm going to try and draw a vesicle attaching here. I'll probably do it poorly. So when the vesicle first, it could make a small pore, right, and a little could come out, or it could make a big pore and release a lot of contents. And so, Andy Ewing's group, Christian Amator's group, Dave Sulzer's group, other people have done a lot of amperometry and then a lot of kind of biophysical experiments to look at, okay, what's going on here where it just opens a little bit, or what's going on there when it opens kind of and we get more like a full spike. So that's this picture, right, and this is that picture. So that's what people have done with amperometry. Pretty interesting kind of work, but the reality is there's limits to amperometry, right? Almost nobody puts an electrode in a brain and just holds to the constant potential. A full brain has too many things in it, right? And so you're not going to get any selectivity, right? So there's no selectivity for amperometry. Anything that could be oxidized at the voltage you apply is going to be oxidized. But at a cell where you know what's going to be in those vesicles, it's a great experiment. It's faster, it's cleaner. As I said, you can get out some of the vesicular release things and that kind of thing. The other, as I said, so the primary uses, I think, are single cell amperometry. And now they even go inside of cells and sometimes inside of an organelle, but it's the same concept. The other thing amperometry is used for is as a detector for separations. And so separations like LC, or we've done capillary electrophoresis, there you don't care about the selectivity as much because hopefully you separated everything into peaks, and then you can just apply a voltage and go there.